All right, so we already did number one was there's two CLs and they're each 35.45, so that came out to be 71.9, 70.9. Okay, so that's how many grams are in 1 mole of that. We also did UF6. So U, there's no number after it, so it's just 1 time, and F is 6 times. So we looked at those masses. What was the answer? Just tell me the answer.
It was 1, 1, 2. I got
What was it?
352.
352? Is that right for that? Well, so you had U. Oh, I was asking for like the whole mass.
Oh.
Yeah. All right, so that was that one. Cool. All right, so number 2, KOH. Every capital letter is an element. So there's a K, there's an O, and there's an H. So if I look up K just one time, that is 39.1 or 39.10. O is 16.00, and H is 1.01. So if I add those up, what do we get? Right? Everybody got that? SO2. So S, no number after it, just means 1. O, there's 2 of them, each at 16. So a total of 32 for that. S is 32.07. So add those together and I get 64.07 grams per mole. So how many grams? 1 mole of that is. All right, BeCl2 would be 1 Be, Cl 2 times. We just used that one not long ago. It's 35.45. Be is 9.01. So 2 times 35.45 is 70.9. I saw that from number 1. And if I add 9.01 to that, I'm going to get 79.91, right? All right, H3PO4. So there's a capital H 3 times, P just 1 time, and O 4 times. So H is 1.01, so that's a total of 3.03 for that. P for phosphorus is 30.97. And O is 16, so that's a total of 64. So I'm going to take 3.03 plus 30.97 plus 64, and I get 98. So 1 mole of H3PO4 would be 98 grams. All right. FeCl3, that's Fe 1 time and Cl 3 times. So I know Cl's mass already. We've used it a few times. Fe is 55.85. So if I take 35.45 and multiply it by 3, I get 106.35, and then add iron, 55.85, and I get 112.2. Good? All right, I kind of laid out number 11, but I don't think I gave you the answer to it, did I? So anything in parentheses with the number outside, what that means is take that number outside and multiply everything inside by that. So n does not have a number after it, so that means 1n, but since it's in parentheses and there's a 2 outside, that actually means there's 2 of them. H, instead of being 4, there are 8 of them. And then outside the parentheses, just normal. So S 1 time and O 4 times. Question? Number 4. Yeah, it looks like my answer is too small. 35.45 times 3 is 106.35 plus 55.85 is 162.2. Thank you. All right, number 11. So nitrogen 2 times, each nitrogen is 14.01. So that's going to be a total of 28.02. Each hydrogen is 1.01, but there's 8 of them for a total of 8.08. Sulfur is 32.07, and there's just one of them. And oxygen is 16, and 4 times 16 is 64. So I got to add all those up. 132.17 grams per mole. All right. And I'm going to go ahead and erase this so I can move down to number 5. All right, so BF3, there's just one B, and there's 3 Fs. So B is boron, number 5. It has a mass of 10.81. Fluorine has a mass of 19. I got to do 19 3 times, which is 57. So I should get 67.81 grams for that. Everybody agree? Number 12 is weird the way they did this. But so C, instead of just being 1, there's actually 2 C's in it. H, instead of just being 3, there's actually a 4th one over here. And O, there are 2 of them. So carbon has a mass of 12.01. I'm going to do that twice. So that's 24.02. Hydrogen is 1.01, so that's 4.04. And oxygen is 16, so it's really a total of 32. So I get 0.06, 8, 10, 3, 60.06. All right. Here I have C just one time, Cl2, F2, so 12.01 and 70.9 and 38. 120.91, is that correct? All right, over here we have PB. It's outside the parentheses, so just normal means one time. We have N and O in the parentheses. So N would be one time, but since there's a 2 outside, there's actually 2 N's. O has 3, but since it's in the parentheses, I got to do 3 times 2, so there's actually 6. I checked these, and number 13 was one of those that a lot of people had made errors on, so make sure you check your number 13. All right. So PB is, where's PB? Number 82, 207.2. And nitrogen is 14.01, is that right? And oxygen is 16. So really I'm going to have 207.2 plus 28.02 and 96. 331.22 grams. Okay. All right, here, Mg, just one time. O and H are in the parentheses, so I got to multiply them both by what's outside, which is 2. So O, instead of being 1, is actually going to be 2 times. H is actually going to be 2 times. I know their masses already. Use them quite a bit. Mg is 24.31. So I've got 24.31. I've got 32. And I've got 2.02. So 0.33, 68, 58.33 grams. And then we've got Ga 2 times. We've got S, we've got O. S is 1 time in the parentheses, but there's a 3 outside, so I got to multiply that by 3, so 3 of them. O, 3 inside, and then times 3 would actually be 9. Has a mass of 16. Ga has a mass of 69.72. And sulfur was 32.07. All right, so gallium, Ga, is actually going to be 69.72 times 2, which is 139.44. And then sulfur is going to be 3 times 32.07, which is 96.21. And oxygen is going to be 144. All right. Yep. All right. So I'm going to add those up. So I've got 139.44 plus 96.21 plus 144. And I get 379.65. Is that correct? That's how many grams are in 1 mole of that. And we know that 1 mole is 6.02 times 10 to the 23rd, right? That's how many particles are in a mole. That's not what you got for the last one? Is the first part right? Did I get the masses right? 2 times 69.72 is 139.44. 3 times 32.07 is 96.21. 9 times 16 is 144. Add those up. Oh, you got it? Okay. So can I erase this up here? Exponents. When we've got parentheses, you mean? Oh, you're talking about the next side? Is everybody good with this last one? All right. So what I want to work on today is actually trying to figure out if we have a certain number of moles, or sorry, particles, trying to find out how many moles that would be. So this is going to involve our scientific notation. All right. So we're really going to try to find the moles, try to calculate the number of moles. Writing this down on the board so we have our success criteria. From number of particles. So our particles, depending on the substance, they could be atoms, they could be molecules. Usually those are the only two I use. Sometimes you'll see this thing called formula units fairly often. Can anybody tell me the answer to the first one? How many moles of water does 6.02 times 10 to the 23rd molecules represent? Number one there. Isn't it just one? Isn't it just one? That's okay. So if you don't have this yet, make sure you've got it right now. 1 mole is 6.02 times 10 to the 23rd particles. So if I say how many moles of water does 6.02 times 10 to the 23rd molecules represent, that's 1 mole. So anytime we deal with particles, we are going to use this relationship. So whenever we deal with particles, we got to use this understanding that 6.02 times 10 to the 23rd particles are 1 mole. It's like the ratios we were using. So whenever you see anything that deals with particles, you are going to think this. Oops. And I'm just going to write atoms, molecules, formula units per 1 mole. That's the equivalence there. All right. Well, what if we don't have that many? What if we've only got 3.01 times 10 to the 23rd molecules? Well, first of all, we can make a prediction if we know scientific notation. If I have 3.01 times 10 to the 23rd molecules, do you think that would be, is that a mole, first of all? No. Is it more than a mole? Is it less than a mole? All right, so we're going to end up with like some fraction or some decimal of a mole, right? I'm going to write this ratio down that I know right now. I want to think about this. I like to abbreviate molecules, MCS. For one, that's how many are in 1 mole. I want to think of this equivalence. There's 6.02 times 10 to the 23rd molecules per 1 mole. So how many molecules, I'm sorry. So I'm going to keep it the same. If I have molecules on the top over here and moles on the bottom over here, I'm going to keep it the same way when I write this relationship. All right? So if I have 3.01 times 10 to the 23rd molecules, how many moles would that be? That's what we're trying to figure out. Yeah, so what we got to do is we got to try to solve for this thing. And I'll show you a couple different ways to do this. So this is just by comparing the ratios. This is one way to do it. All right. You might like the second way I show you better. I probably will. Now, if I try to solve for something, the first thing I got to do is I got to make sure it's on the top part of the equation. Right now, it's not on the top part of the equation. So I think what I'm going to do, and the general rule is when you deal with an equation like this, whatever you do to one side, you have to do to the other side. Okay? So I would rather have moles up on top. So what I'm going to do is flip everything around. So instead of putting 6.02 times 10 to the 23rd molecules per 1 mole, I'm going to say 1 mole per 6.02 times 10 to the 23rd molecules. And that's going to equal how many moles per 3.01 times 10 to the 23rd molecules. Okay? So now the thing I'm solving for is on the top part of the equation. Just watch, you'll see. So now the second thing is I got to get this by itself. All right, it's not by itself right now. It's being divided by 3.01 times 10 to the 23rd. So what I'm going to do is I'm just going to multiply both sides times that. Because if I do that, it'll cancel this out. Yep. I'm going to show you, I'll do another example. And I'll show you a way that you might like better. All right. So you probably don't like that way. So what we end up with is we end up with 3.01 times 10 to the 23rd molecules over 6.02 times 10 to the 23rd. Almost. How do we divide scientific notation? Divide the front numbers normally. If I do that, I'm going to find out that that is 0.5. The next thing I'm going to do is write times 10. And then I'm going to subtract the exponents. What's 23 minus 23? 0. Do you remember what any number to the 0 power is? 1. So really it's 0.5. You could leave it at 0.5 times 10 to the 0. Or you could put it as 0.5 times 10, or sorry, 0.5 times 1. Or you can just leave it as 0.5. All right, so that's like comparing using ratios. Now, the other way to do it is dimensional analysis. Again, I can't stress this thing enough up here. This is our tool for solving all these problems, regardless of the method we use to solve the problem. Okay? So one thing I had mentioned to you before is that we can look at the problem itself and we can see what's given to us. So in number 3, they're asking us how many moles of glucose does 1.2 times 10 to the 24th molecules represent? What they're telling us is that there's 1.2 times 10 to the 24th molecules. The thing that is given to you in the problem I call the start, meaning I'm going to start my equation with that. So 1.2 times 10 to the 24th molecules. Okay? You could just leave it like that. I also like to put it over 1 just so I can clarify that that's on the top part of the equation. But anything over 1 is just that thing. Notice, by the way, no units on the bottom there, just over 1, just saying it is what it is. It's the thing that's given to us at the start. Now I'm going to write times. And what I'm going to do here is I am going to use my conversion factor. My conversion factor is my tool. It's a relationship I know. It's this thing I marked with the little asterisks and I put a box around. That's the tool I'm going to use for all these problems. Now, I might use it the way it is, 6.02 times 10 to the 23rd particles per mole. Or I can say the same relationship by flipping it upside down and saying that there's 1 mole per this number of particles. Okay? Now, which way do I want it? Well, when we do this type of problem using this method called dimensional analysis, whatever units I have right here, I want those same units to be down here. Well, in order for molecules or particles to be on the bottom, I have to flip this thing upside down. So instead of putting the 6.02 times 10 to the 23rd on top, I'm going to put it on the bottom. And instead of the 1 mole being on the bottom, that's going to go up to the top. This one? This is the method I prefer, but sometimes students struggle with it. So yeah, this is what I would do. So the reason is, the idea is that whatever units you start with, you want to cancel out. And you want to try to get some new units, whatever units they're asking you to find. In this case, moles. So now that I have molecules on top and on bottom, they cancel out. So now the only units that are left in this problem are moles, which is good because that's what we want to find. So now I'm just going to multiply across the top, which is going to be 1.2 times 10 to the 24th times 1, which is just 1.2 times 10 to the 24th. I do have units up there still called moles. And on the bottom, it's just 1 times 6.0. It's just 1 times Avogadro's number, so it's just going to be Avogadro's number. So now we got to divide scientific notation. So I'm just going to take the front number, divide those. So 1.2 divided by 6.02. And that comes, that's not right. 1.2 divided by 6.02 is 0.199. I could probably just write it as 0.2. And then I'm going to write times 10. And then I'm going to subtract the exponents. 24 minus 23, which is 1. That's how many moles I have. So if I had 1.2 times 10 to the 24th molecules, that would be 0.2 times 10 to the first moles. Like I said, when you get those low exponents, you can start to really just think of it maybe as a normal number. Like 1 as an exponent. Really, 10 to the first is just 10, isn't it? So really, it's like 0.2 times 10. Really, it's just like 2 moles. So what would our start be for number 4? What is it? Okay, they say formula units. I really just think of formula units as molecules. You could write formula units if you want. Put that over 1. Again, I'm going to use my tool. 6.02 times 10 to the 23rd molecules per mole. But again, if I've got molecules on top, then where do I want to put Avogadro's number? On the bottom. Okay? So the molecules cancel. And if you have that, I'm going to let you just do the math on that in a little bit. I want to show you number 5 because number 5, they don't give us the particles. They give us the moles. And I'm going to do it the 2 methods like I did before. But you don't have to write anything until I'm done. So you can decide which one you like better. Okay? But I do need to erase this. Can I erase that? So number 5, and I'm going to go ahead. I want to write this relationship down again just so I don't forget. Again, we got to understand that particles could be atoms, they could be molecules, could be formula units. So I know every time I'm either using that or I'm using this. Whatever cancels out my units. Okay, so don't write anything for number 5 yet until I'm done. See what you like. But the comparison method for this, if I've got 2 moles and I want to know how many atoms, so it'd be like how many atoms are there in 2 moles if I know there are 6.02 times 10 to the 23rd atoms in 1 mole. Okay. So if I wanted to solve for number of atoms there, I would just multiply both sides by 2 moles. That would cancel that. So how many atoms equals Avogadro's number times 2 moles over 1 mole? That's pretty easy. So 2 times 6.02 would be 12.04 times 10 to the 23rd. I have moles on top and on bottom, so those are gone. So that many atoms. I could change that to 1.204 times 10 to the 24th as well. So that's one way you could do it. But really, if you learn my dimensional analysis way, it's not mine personally, I didn't invent it. But if you learn it, it's going to be just as easy as this every time. Or sometimes, especially like you saw in the first 4 problems, usually easier. So what I would do What's given to me in the problem? The moles. How many? 2.0 moles. Now, in this case, if I look at my conversion factors, which one do I want to use? The first one or the second one? The second one? Why would I want to use the second one? Okay, if I wrote the second one, would the moles cancel out? Okay, so always remember when we're setting this up, whatever units I have to start, I want those units on the bottom here. All right, so you like the first one better? If I write the first one, I'm going to end up with 6.02 times 10 to the 23rd particles, which in this case, you can write this, yes. In this case, we're talking about atoms, and then I'll put the 1 mole on the bottom. So remember, when we're setting these up, the main idea is that we want to cancel those units that we're starting with. So they got to be on the bottom of the conversion factor. So here I canceled out moles. I have atoms. That's what we're trying to find. So it really just works out the same way. I'm going to end up with 2 times 6.02 times 10 to the 23rd over 1. So it's going to end up being 12.04 times 10 to the 23rd atoms, or 1.204 times 10 to the 24th atoms, just like we got before. All right. But I think that's probably the easiest way to do these. And I want you guys to take the next 18, 21 minutes, 20 minutes. See how many more of these we can get done. How many more do we have? See if we can get the last 3 done. All right? Work together, work on your own. It's up to you.